Welcome to Dr. BT's Chemistry Essentials, A-Level Chemistry made easy. In this video, we're going to be looking at the rate determining step and using that rate determining step to find out some information about the rate equation and vice versa. Okay, so let's take this typical reaction where we've got nitrogen monoxide, 2 moles of it reacting with oxygen to form 2 moles of nitrogen dioxide. Now, as we've looked at previously, we can interrogate the effect of each of these reactants on the rate. So firstly, we could vary the concentration of the nitrogen monoxide, and then we might come up with the effect that this concentration has on the overall rate of reaction. We then find out that as we double the amount of nitrogen monoxide, we find that we actually get the overall rate of reaction quadrupling, so timesing by 4. So this tells us that it is second order with respect to the nitrogen monoxide, because as we doubled this, we get times 4 over here, which is the same as saying times 2 to the power of 2. And it's this power that tells us what order of reactant it is. And so we know that the rate equation is going to look something like this, but we know we also need to work out whether or not the other reactant, in this case, oxygen, O2, has any effect on the overall rate of reaction. So you'll follow the same flowchart, but this time with the reactant O2. But with this reaction here, once we vary the concentration of the oxygen, we find that the rate does not change. This is the same as saying it's whatever effect that you're doing on the reactant oxygen here, it's doing that to the power of 0 because it has no effect on the actual overall rate reaction. And so with this being 0 order, it does not appear in the overall rate equation. But when you think about it, this is quite strange because surely whenever we've talked about collision theory, we take this reactant and collide it with this reactant and then that forms a new product. So surely oxygen should have something to play with determining the overall rate of reaction. So surely there should be a term here. However, this doesn't just happen in one step. I'm going to show you the 2 steps that happen in this mechanism. So the first step takes the reactants, and there's 2 moles of these, and these are where those 2 moles are, of the nitrogen monoxide, and they collide together to form this N2O2. It's then the product of this that then moves into the second step. This then reacts with oxygen and forms 2 moles of NO2. So we can see there are 2 steps that make up the overall equation up here. So we're basically just deconstructing what this all means in here into its individual parts. Now, each of these steps, step 1 and step 2, have different speeds. One is always going to be relatively slower than the other. Now, in these cases, we're going to have a slow step and a fast step. And chemists can use the overall rate equation in order to determine which of these steps, 1 or 2, is the slow step, and therefore which one is the fast step. Also, if you have more than 2 steps in your stepwise mechanism, there will always be one that you term as the slowest step, also known as the rate determining step. Now, the reason it is called a rate determining step, this slowest step, is because the speed at which this step occurs at determines this here. Whilst it says rate here, this is the overall rate of reaction. And remember, it's the overall rate of reaction that you measure. So a good analogy for this is to imagine a school corridor. And what we're imagining is our student has just taken French and has to make their way to their chemistry lesson. Now, the rate of reaction, the thing that we're measuring here, is the time it takes for this student to leave French and make their way to chemistry. So a fast rate of reaction would be going from here to here, so the overall rate would be fast, they're getting there on time. Now, if we take this same analogy, but imagine we've got this in 2 steps. So it's not just one big run like this equation suggests. This being our chemistry classroom, this being our French classroom. Instead, there's 2 steps within it. Step 1 is just taking the little distance from here to these set of double doors. Step 2 is then the way to the actual chemistry classroom. So these double doors are going to be important because whenever you move classrooms during a changeover, there's lots of other people doing that as well. So there's always a bit of traffic along this corridor. Now, step 2, imagine these double doors aren't open. Only one of the doors are open. So when our student leaves at classroom changeover time, then there's lots of people in the corridor. Going from here to the double doors is fairly easy. There's lots of space. So this is our fast step. But then when our student actually gets to the double doors, there's a bit of congestion because everyone is being bottlenecked into this one open door. So this congestion is really slowing them down. So step 2, which is designated here as this double doors, is going to be slower. And so it is this slow step that determines how fast our individual gets to the chemistry classroom. So it is the slow step that directly affects the overall rate of reaction because this is so fast, it's all bottlenecked here. Now, another analogy is to think of the processes that happen when you get out of bed in the morning. So in this analogy, the overall equation is the alarm going off, being the reactants, and the products being you out of the door. Now, within this, though, we know there are multiple steps, our stepwise mechanism. There's you waking up from that alarm. There's you then going into the shower. There's you then eating some breakfast. There's you then brushing your teeth. And then there's you actually leaving. Now, some of those are going to be quite fast, and one will be the slowest one, and that will determine the overall effect of your leaving the house. Now, as chemists, with any of these reactions, we need to work out which of the 2 steps are the slow or the fast. And the way you do that is you look at the rate equation. So the rule to take from this is that the reactants which appear in the rate equation are the reactants that appear in the rate determining step. So in this example here, our rate equation is telling us that we've got nitrogen monoxide, and so it must be this reactant that appears in the rate determining step. Now, I just want you to pause the video here and see, can you identify which one of these, step 1 or step 2, is the rate determining step based on this piece of information? Okay, so we've got NO as the only reactant that's in the rate equation. You can see here, step 1 has NO reacting with another NO, so that fits. But step 2 has N2O2 plus O2. So that does not fit at all because we've also got oxygen here and we've got this particular species. So if we were to assign these, this is going to be our slow step, and then step 2 is going to be our fast step. The other thing to note is that in your rate equation, the order of each reactant tells you how many moles of that reactant are in the rate determining step. So here we had 2 moles of NO, and you can see here we had to have 2 moles of NO reacting with each other to form N2O2. So this all fits. Now we can use this same relationship to work backwards. So if we are told that step 1 is the rate determining step, then we know to look at the reactants, and we know how many moles of that reactant there is. And so we can come up with the rate equation for that. So here we've got 2 NOs, hence square brackets NO to the power of 2, because the reactant order tells you the number of moles in the rate determining step. So let's look at this reaction, where these reactants are converted into these products. Now there's 3 steps within this mechanism. Now these steps are going to be unusual chemistry. Don't worry about that, we're just looking at the principles here. Step 1 uses up the reactant to form this intermediate. This then gets used up in the second step and breaks down and decomposes into two parts. And then this then feeds into the third step, reacts with the iodine to form our two products up here. Now, given the information with the labels on each of these arrows, I want you to pause the video using the information we've talked about to come up with a rate equation for this reaction. So pause the video now and see if you can have a go at this. Okay, so you should have only focused in on this equation here, our slow step. Now, we'll look at some more complicated examples later, but there's nothing preceding this, so this is the only equation we need to focus on. These two fast steps aren't going to have anything to do with the rate equation, so we can instantly remove those from our focus. Now, when we then focus in on the reactants in this step, we know from this information here that only reactants that are in the rate determining step appear in the rate equation. So iodine isn't going to appear in the rate equation, but because this is in the slow step, this ketone, this will appear. And furthermore, this H plus will also appear. So it's worth noting here that just because something's a catalyst doesn't mean it cannot appear in the rate equation. As long as it is in the actual reactants of that particular slow step, then it will appear in the rate equation. Now, the other thing to notice is the reactant order that we're going to put in our rate equation here and here is all down to the number of moles in the rate determined step. As we only have 1 mole of the ketone and 1 mole of the H plus ions, then this rate equation is perfect as it is because they're both to the power of 1. And as a side note, it's really important just to think, well, iodine is a reactant. It doesn't appear in the rate equation, so it must be 0 order. So any reactant that is 0 order must appear in a fast step. And you can see iodine here is in this fast step. So they do still are involved in the reaction, but just not in the slowest step. Okay, there's one final piece of information to do with the rate equation and its link to the rate determining step, which will then allow you to answer all questions. So we're going to look at one more example. So in this example, we have 3 steps that make up this overall equation. Step 1 and step 3 are fast, whereas step 2 is our slow step. This information, I would like you to come up with the rate equation for this reaction. Pause the video now and have a go at that. Okay, if you came up with the rate equation of K is N2O2, first order, and H2, first order as well, because these are the reactants in this slow step, then I can see what you've done, but unfortunately that's wrong. The reason this is wrong is because the final piece of information when dealing with rate equations and rate determining steps, and that is, if you are going to put a reactant in the rate equation, that reactant must be something that you can directly measure in an experiment. The things that we can directly measure in an experiment is something that appears in the overall equation. Now you can see hydrogen is in the overall equation, but N2O2 is not. Only NO is. The reason for this is N2O2 is what we call an intermediate. Now intermediates are fleeting. They only exist for a short period of time. They are always produced in one step and then used up in another step. As a result of this, we've got to think of these arrows as an equal sign in equation. They will cancel each other out. Now, as they cancel each other out, they won't appear in the overall rate equation. So, as we've discussed before, they're not a true reactant, so they cannot appear in the rate equation. But obviously, this is the reactant in the slow step. So we're going to look at that in a moment. But before we move on to that, what I want you to do is just pause the video here and see if you can identify another intermediate in these stepwise reactions. Okay, so if you notice we've got N2O and N2O here. It's the product in one step becomes the reactant in the next step. They cancel each other out, so they are intermediates, and that's why also N2O does not appear in the overall equation. So we know N2O2 is a reactant in the slow step, but we can't use intermediates in our rate equation because we can only use reactants that appear in the overall equation, because these are the things we can actually measure using experiments. So instead, we need to take N2O2 and treat this like a daughter molecule. This has come from some parent reactants. So we need to trace the history of how N2O2 was produced. So we look at N2O2 here in the second step. If we go back and see what the parents were of this, then it is 2 molecules of NO. So your task here with any intermediate is to go back steps until you find reactants that appear in the overall equation. Now NO and NO do appear in the overall equation. So really our rate equation, to be correct, should read like this. So the parents of the N2O2 are 2 molecules of NO. So we know that it's second order to NO. And then also we've got hydrogen here. So these reactants that you put in the rate equation must be in the overall equation. So it's always worth checking. So if you wrote this out, you'd look at N2O2, you'd just check the overall equation. You can see hydrogen's in there, so that's absolutely fine. That's why we kept that. But you can see N2O2 isn't. So we have to then go searching for the parent molecules, and those parent molecules should be the ones that appear in the overall equation. Okay, so now we're just going to practice this key concept. So pause the video here and see if you can come up with the rate equation for this reaction. Okay, so we know that our slow step is step 2 here. We know that we have B and C as our reactants, and we can be happy to include C in our equation because it's also in the overall equation. There's only 1 molecule of C involved, and we know that that therefore means that the reactant order is first order. B, on the other hand, does not appear in our overall equation as a reactant, so it is an intermediate. So we must search for these parent molecules. So if we look backwards, and we could tell it was an intermediate because it was both created and used up, we can see that that is formed by 2 A's colliding. So using that and the fact that A appears in the overall equation, and the fact that it took 2 molecules of A to create B, means it's going to be second order. Now, I just want to debunk any relationship that you think that the overall equation and the stoichiometry or the molar ratios of the reactants has with the rate equation. Just because we have a 2 here in front of A doesn't mean that it's second order here. And just because there's 1 mole of C doesn't mean it's first order here. This is just a coincidence, and you should never make that link, as the powers here have no relation to the molar ratios in the overall equation. Okay, so let's put some of these principles in practice. What I'd like you to do is pause the video now, have a look at this exam question, and see if you can come up with a rate equation that is consistent with this mechanism. Okay, if you chose C, then that's the correct answer. The reason being, we need to focus in on our slow step and the reactants of that slow step. So we can see here we've got NO2 and NO2. Now, here we've got NO2, NO2, but then they've also given carbon monoxide. Carbon monoxide isn't a reactant here, so that eliminates options B and D. And then we're left with A and C. Now, C is the right answer because it's to the power of 2, and that links directly with how many molecules of NO2 are in the slow step, and there's 2 molecules here. Whereas this would only fit if there was 1 molecule of NO2 in the slow step. So this exam question, which is the final one of this video, is going to use some of the skills you've looked at in previous videos. So determining the rate constant, and then it's going to use a slightly new skill here, but it's the link to everything we've been learning today to come up with and propose a two-step mechanism that fits with the rate equation that you come up with when you've looked at the initial rates table. So this is 6 marker. It's quite difficult, but pause the video, have a go, and if you're struggling, don't worry, we're going to go through it. Okay, so in order to determine the rate constant and the two-step mechanism for this reaction, we need to come up with a rate equation that fits this data in this initial rates table. So focusing in on the ozone, the O3 reactions here, we can see that experiments 1 and 2 have remained constant, so that's a good one to compare here. This has times by 3 in terms of the concentration. And then we also notice that the initial rate has times by 3. So we know that it's first order with respect to O3. Knowing this information, we can then turn our attention to nitrogen dioxide. Here, experiments 2 and 3, the ozone is constant, whereas NO2 we've doubled between experiments 2 and 3. And as we double this, we notice that the rate also doubles. So it's again proportional, so it's first order with respect to NO2. So with that, you've kind of got your first 2 marks of this 6-mark question. We have got an equation here, and we want to work out the rate constant. So we're just going to rearrange to make K the term. If any of this is unfamiliar, go back and make sure you watch the videos on the rate equation. And all that remains now is to substitute in the values for each of these terms in order to work out K. Now you can choose any of the experiments 1, 2 or 3 to do this. It should give you the same value for K. For example, if we would choose experiment 3, then rate would be 1.92 times 10 to minus 7. You divide that by the concentration of ozone, which is the 3 times 10 to the minus 3. It's to the power of 1. Because it's first order, as we worked out in its relationship. And then NO2 would be this number here. Now, when you put that all into a calculator, you will get the answer. That secures you the third mark out of the 6. The units, all you need to do is find the units from the table. So we've got rate here from here. We've got 2 moles per decimeter cubed, the first order, so we don't need to do anything with powers here. Cancel this down. So taking 1 away, there, then we're left with S minus 1 over mole per dm minus 3. We want to invert this so that we get concentration on the top line. And that changes, this was mole to the 1, becomes minus 1. dm minus 3, as it goes on top here, it becomes 3. And so that gives us our units. And that is secured as our 4 marks. Now all that remains is that we need to use the rate equation we've deduced with the overall equation in order to come up with a two-step mechanism. So this can be quite difficult and it sometimes requires a bit of trial and error, but we know it's two-step mechanism. So I've just done 2 steps here with our reaction arrow. We also know that these are reactants that we need to use up and these are products that we're going to form. Anything else that is on this side and this side will then cancel down as an intermediate. But importantly, one of these steps is going to be slow. And the reactants for one of those steps is going to be O3 and NO2 because they both appear in the rate equation. Now, if we take our slow step and take out an O3 and an NO2, then we know in our fast step, we must have 1 mole of NO2. So you can see here, I've designated step 1 as slow to fit the rate equation here. O3 and NO2, so that's used up that O3 and one of those NO2s, got my NO2 remaining, so I'm going to put that in the other step that we're going to call the fast step. Now I'm going to turn my attention to the products of the overall equation. Now these mean that the products here and here are going to have to match up with this. Now any products of 1 that get used up in step 2 as a reactant is an intermediate and so won't appear in the overall rate equation. So we need to take that into account. Now, just focusing on N2O5, you can see that's made up of 2 atoms of nitrogen. Well, in this step here, I can only introduce 1 atom of nitrogen because I've only got 1 NO2. So whatever the intermediate here is that drops down into here is also going to have to contain a nitrogen. And then that nitrogen is going to have to then combine with the nitrogen of this second NO2 to give me that N2O5. There's just no way I can get 2 nitrogen atoms as the product of this step because I've only got 1 on this side. Now this then gives us a hint. We've got 5 oxygen atoms here and only 2 oxygen atoms here. So this must contain an O3. This also seems sensible because this is nitrate, NO3. We've seen that before, and this is nitrogen dioxide. And that would all balance out. So I don't need to add anything extra here. And that links to the overall equation because I've produced that molecule of N2O5. Now my other product in the overall equation is oxygen, O2. So I need to account for that. So we're definitely going to have an O2 produced here because for reasons we've already spoke about, it can't be the product here because otherwise these wouldn't balance. Therefore, when we add the O3 and the NO2 and they collide together, they're producing oxygen and then they're producing another species. Now that other species we've already worked out because we worked out NO3 would fit in here. So we're going to just put an NO3 here. So this is a really sensible suggestion for this. You could have also come up with another one. So the first step of this alternative is O3 and NO2. So this is our slow step because it matches the rate equation. It produces 2 molecules of oxygen and a nitrogen monoxide molecule. Now with that in mind, we can only, because of the overall equation, produce 1 mole of oxygen. So one of these needs to get used up in the second step. Also, this nitrogen monoxide is not in the overall equation, so that must be an intermediate too. So this must be used up in the second step also. We know one of the products is N2O5, so let's put that on the right-hand side of the second step. Then all that remains is that because we've got 2 nitrogens on the right-hand side and only 1 on this side, we need to add in another species of nitrogen, NO2. That then matches up because we've got 1 mole of ozone accounted for in step 1. The 2 moles of nitrogen dioxide, they're in the overall equation. There's 1 there and 1 there. Obviously, the NO and one of the O2s here is an intermediate because then they're used up in the second step, so they cancel out. That then leaves 1 oxygen molecule. And then finally our N2O5 molecule here. So both of these can fit the equation. So this concludes the video looking at rate determining steps and how they link to the rate equation. If you found this video useful, ensure that you like the video and then ensure that you hit subscribe so that you can subscribe to further new videos as and when they're uploaded. The next video we'll be looking at is using this idea of rate determining step and the rate equation in order to differentiate between 2 different mechanisms in an organic chemistry problem. So it's very synoptic, it's a common exam question, so ensure that you watch that one.